So we've got two spacecraft here, and I've labelled them A and B, and they're moving in opposite directions to one another. An observer on Earth measures the speed of spacecraft A to be 0.500 of the speed of light in the positive x direction. And the speed of spacecraft B is a negative 0.5 times the speed of light. So if you were a crew member on spacecraft A, what would be the velocity of spacecraft B according to you while you're in spacecraft A? So in other words, how fast would spacecraft B appear to move past you? Well, there is an equation called the Lorentz velocity transformation equation, and we use this for these types of relativistic problems. And I'll explain what all the variables mean in a minute. Now, if we didn't know about special relativity, we'd believe that spacecraft B is appearing to move past us at the speed of light. And I'll give you a quick everyday example of this. So if you're driving on the road at 30 miles an hour and another car is driving in the opposite lane towards you, also at 30 miles an hour, that car would appear to speed past you at 60 miles an hour in your frame of reference. But as we move at speeds that are a significant proportion of the speed of light, things get a bit strange. So the speed of spacecraft A, I'm going to assign to the variable v, and u sub x will be the speed of spacecraft B according to me in my frame of reference. So the second observer is going to be you, and you're on spacecraft A. And you get a different measurement for the speed of spacecraft B, and you assign it whatever the speed is with the variable u prime sub x. So now we can plug in the values to see how fast you think spacecraft B is moving past you according to your frame of reference. So plugging in the values to the Lorentz velocity transformation equation, the c squared variable cancels out in the denominator at the bottom here, and when we sum all of this up together, we get a negative 0.800 times the speed of light. So you in spacecraft A, instead of viewing spacecraft B moving past you at the speed of light, as you would expect in classical physics terms, according to special relativity, it would be moving past you slower than the speed of light. So we're going to try a different variation of this problem now that normally catches people out. And it catches people out because they incorrectly assign the velocities to the wrong variables in the Lorentz velocity transformation equation. So with this question, you happen to be in the Earth's reference frame now, on the left-hand side here. And let's say that you're in mission control, and we're going to simplify this, like the previous question, and assume the Earth is at rest. I'm in a spacecraft now, travelling to a planet we've recently discovered, and we're calling this Planet 9, for example. My craft is moving at a constant velocity at 0.80 times the speed of light, which you can see on the right-hand side in this reference frame here. But 10 hours into our journey, or into my journey, I decide to send a probe towards Planet 9 at 0.70 times the speed of light relative to my spacecraft, or relative to my frame of reference. So according to me, I've shot off a probe to Planet 9 at 0.7 times the speed of light. But how fast is this probe going relative to you on the Earth? And it might be important for you to get the speed of this probe relative to you on Earth so you can account for the Doppler effect in the radio communications between the probe and the Earth. The variable u sub x must be the speed of the probe relative to your reference frame on the Earth. Now we can see here that our Lorentz velocity transformation equation needs to be rearranged to make the u sub x the subject of the equation. Now I'm going to speed through this quickly, but pause the video if you want to check through the working yourself. So we've made u sub x the subject of this equation by rearranging the Lorentz velocity transformation equation. And we can now plug in our correct values. Now, according to you, on Earth, the probe is moving at 0.96 times the speed of light. So if there wasn't a speed limit in the universe, and if we could view physics classically, then the speed of the probe would be faster than the speed of light if we view things classically. But we can't actually do that in modern physics because nothing can go faster than the speed of light.